bubble sort. This video is going to take us through what a bubble sort is, how efficient the bubble sort is, programming a bubble sort, and that will include using static data structures. So we're going to be looking at an array. So again, static data structures are ones that don't change in size once they're declared. Some nested for loops. Nested meaning one programming structure within the other. So it's going to be a for loop inside a for loop. And we're going to also see some random numbers for programming our bubble sort in order to test it effectively. Okay, jumping straight into this. The operation of a bubble sort. So here we have an example of an array with 5, 3, 8, 4 and 6 in. So initially it's unsorted. What the bubble sort will attempt to do is obviously sort it, and it does it by comparing pairs at a time. So what it's going to do is compare the first two pairs, the 3 and the 5. Because we're doing this in ascending order, we know that the 3 has to come before the 5, so we make a swap. So we swap them over. Then we repeat that, checking of the pairs, on the next two. So the 5 and the 8. The 5 isn't greater than the 8, so actually they're in relation to each other, they're in the correct place. The next step, the next pairs, the 8 and 4. They are different, so we are going to swap those. Sorry, the 8 is bigger than the 4, so we are going to swap those. And then we check the next pair, the 8 and the 6, and swap them, because 8 is greater than 6. And we actually get to the point there, after doing those 5 steps, that we know that 8's in the correct position because the largest thing must have moved to the right hand side. We must have moved the right hand side. We'll notice that the rest of the array isn't sorted yet, but that's because we've only been checking pairs of things, and we'll have to then repeat these steps again. Sorry, not to the initial, to step 1. Repeat these steps, and if we keep repeating those steps, eventually it will be sorted. And we'll keep repeating until no more swaps are required. Now, the worst case scenario for this would be if the array was initially sorted the opposite way to which we want it to be sorted. So we'll take you through that. So if the array was descending order here, so we got 8, 6, 5, 4, 3, that would be the worst case scenario to sort in ascending order, because we would have to change every single one of the numbers. So the bubble sort's going to take those pairs and swap them and swap them and swap them, but we're going to have to repeat that a number of times. Now we're not going to show all of the different pairs being compared, but what would happen when we start to check this one, the 8 would compare to the 6, they would swap. Then the 8 would compare to the 5, then they would swap. Then the 8 would compare to the 4, and they would swap. Then the 8 would be compared to the 3, and they'd swap. So you'd end up with an array that looked like that. So we've shifted the 8 all the way to the right hand side. So that step 1 to 5 that we looked at there, that comparing pairs, one full cycle of that would give us this array. Now we need to repeat that process again, hence why we're going to have for loop within a for loop. We're going to have this for loop to test all the different pairs, and then a for loop to make that testing of pairs go round again. So what will happen this time, 6 will compare to 5, they'll swap. 6 will compare to 4, they'll swap. 6 will compare to 3, they'll swap. 6 could compare to 8, but we do know that 8's in the correct position, so we could we could make the algorithm a little quicker, but for now, compare to 8 and they would not swap. So you end up with 6 over here now, and the array looking like this. And it will continue to do that. 5 to 4, swap. 5 to 3, swap. 5 to 6, no swap. 6 to 8, no swap. And then 4 to 3, swap. 4 to 5, no swap. 5 to 6, no swap. 6 to 8, no swap. And then you get the array in the correct order. And if you go across and make no swaps the whole way, it's sorted. So 3 and 4 wouldn't swap. 4 and 5 wouldn't swap. 5 and 6 wouldn't swap. 6 and 8 wouldn't swap. It is in a sorted order. How many comparisons could there have been? Well, this is an array of size 1, 2, 3, 4, 5. So an array of size 5. So the number of elements is 5. And to do any one of the swaps going from one to another here, we were making 1, 2, 3, 4, 4 comparisons, 5 comparisons. Comparing it once, twice, 3 times, 4 times. Yeah, we were making 5 lots of comparisons, and we were doing that 5 lots of comparisons 1, 2, 3, 4, 5 times. So we're going to be doing 5 times 5, so we made a total of 25 different comparisons. Now, how would that change if we had less items? So if we only had 3 items? Well, 3 items, there'd be 3 comparisons 3 times as a worst case scenario. 3 times 3, 9. So as the number of items goes up with a bubble sort, the number of comparisons, the number of computations increases dramatically. And in fact, we can represent this using big O notation to work out how efficient a bubble sort is. And it's just a mathematical notation of the limiting behavior as it tends towards a particular value over infinity. We tend to look at as the elements go to infinity, and we classify it based on their runtime or space requirements. Now we're looking in terms of runtime here. So as the number of elements increases, the number of comparisons, the number of operations, the time it's going to take is going to increase as well. And for our bubble sort, it's n squared, O(n) squared. Because we've got the for loop that goes through n amount of times. So we've got a for loop that goes around n times. And then inside of that, you've got another for loop that goes around n times. So for n amount of times, it's going to do n amount of things. So hence n times n squared. And you see here, as the number of elements increases, it goes up dramatically. We saw the number of operations going from 3 items being 9 different operations it would have to perform to 5 things in our array being 25. It's a big jump. It's not like we've seen in the linear search, which is O(n), where if we were doing a search and it was 3 items long, the worst case finding an item or not finding it would be 3. The worst case for 5 would be 5. That goes up in a linear progression. This is going up in a polynomial as a polynomial form. So we need to be careful when using bubble sort because it's not the greatest type of algorithm as our number of items increases. You see ones down here like the linear search, which goes up in a linear fashion, which is deemed to be okay down there. And we've also see down here that we can't actually see it raise off the ground, but the log n there, which we covered with the binary search, it does grow but starts to level off, doesn't come down, like my drawing should suggest there. But as the number of elements doubles, that only goes up by 1. We proved that in the binary search video, up by 1 for every 2 times the number of elements. So it increases dramatically. But with that increase, you need the data to be in order for the binary search. It needs to be in some sort of order, which we need to perform a sort for that. So we're going to have to use something like the bubble sort, which is not very efficient, as we can see there. So we need to go and program it, and as mentioned before, we use a static data structure, an array. We use nested for loops. We discussed how they impact our efficiency, and we're going to use random numbers to test this out on. Design our program a little bit. We're going to have our sorting algorithms program, and we're going to break it down into 3 subparts here. We're going to generate some random numbers in an array. We're going to have an output of the array so we can see what it looks like, and we're going to have a bubble sort. So we're going to be able to generate a random array of numbers, output that to the screen so we can see it, bubble sort that array, and then we can go and output it again, and we should see that it's been put into the correct order. So we open Visual Studio up, and we make a new project. I've called mine sorting. I'm going to get going with this design. So as in our design, we're going to have three main subroutines. One, the generation of a random array of integers, an array of random integers. So my subroutine is going to return to me an array of integers, and then I need to come up with a name for the subroutine. Random array ints. Random array ints. Random array R ints. In fact, I'm just going to shorten random as well. RND. Random array ints. And I'm also going to pass in an integer of how big I want this array to be, so I can change it up later on. I'm going to declare my random integer array that I'm going to create. Int array, and set it equal to a new integer array of size. Remembering this is a static data structure, so once we've done this and maybe passed in 10, it won't be able to change in size. Passing 100 won't be able to change in size. It's static, it's fixed in size there. And then we need to put in a random integer in all elements of that array. So we're going to use a for loop to go through from 0, our first index in the array, all the way up to the length of the array. Int array dot length. And we're going to be generating our random numbers. So of course we need a random number generator. Random number generators are what they call pseudo-random. You might start to see that that term come up, pseudo-random. It's interesting to look up what pseudo-random is. It uses equations and the system time to generate random numbers. So actually, if we put in seed values in here and we use that same seed value again, we'll get the same range of random numbers coming out again and again. We can prove that later on. So that's our pseudo-random number generator. And then inside our int array at position I, so start off at 0, then as this for loop goes around, increments 1, 2, 3, however long the array is, we want to put in a random integer, random next. Now we can just leave it as next like that, or we could give a max value or a min and max value. I'm going to give a max value of size times 10. So whatever size we put in, so say we put in size 10, we'd make an array of integers, of 10 integers, and then as it goes through this, it will generate a random numbers from 0 to 10 times 10, from 0 to 100. So it gives us numbers from 0 to 99 randomly. If I made the size 5, the array size would be 5, so there'd be 5 integers, and we could have random numbers from 0 to 50, 0 to 49, because 5 times 10, 50. So that gives us our random array of integers, and because it's a function, we're returning array of integers, we need to return the integer array. There we go. So that should generate those for us. And then I said next we wanted to be able to output these and see them. So static void output array, and just going to get it to pass in an array that we wish to output. So output array, and it's just going to be a for loop again to go through the length of the array, and at each stage outputting it. So I'm going to use right rather than right line, which means it goes onto the same line, and just going to have array at position I being output, and then concatenate it with a space after it. So just going to have loads of numbers separated by a space on the same line. And we should test that before we go into any further into our bubble sort. So we're going to have our integer array up here in the main, integer array called int array, and we can name it the same as this one because this integer array is local, a local one inside of this subroutine, and this is local inside of the main subroutine. I'm going to set it equal to the subroutine that we made, random ints, and we'll start off with a size of 5, so you can see it, see and test it works. So integer array of 5 random integers, so that should make, it should go off to this subroutine, put random integers into this array, return the array, and then it should be placed into here. And then we want to output it so we can see it, output array, and we're going to pass in the array that we're looking at. So we're going to pass this through to the output array, and it would console write everything for us. The first item followed by a space, then the second item, third item, fourth item, and then fifth item, because we've gone for 5 initially. And lastly, a console read line, so the program doesn't just flash up and flash down. So it allows us to stop and see what's going on. So run that, and we're expecting 5 numbers separated by spaces randomly generated between 0 and 49. And that's what we get. Make it larger. So it randomly generated the numbers 2, 41, 42, 38 and 45. If I increase this to 8, we should get 8 different numbers. Again, that's in a range now between 0 and 79. So all those numbers are falling in the range, and there are 1, 2, 3, 4, 5, 6, 7, 8 of them. So it appears to be working. The output's there as well. We can see it in action. And just before we move on to the bubble sort, just want to show you that the pseudo randomness. So if you hover over what this version of random does, this overload, creates a new instance of the random class using a time-dependent default seed value. So if you've played games like Minecraft or any game where they generate random maps, sometimes you can get asked for a seed value, and if you use that seed value again, or you give that seed value to somebody else, they can generate the exact same map. That's because those games will be using pseudo-random number generators. And we can use them here as well. So if I put the number 500 in there, I could have chosen any number seed value really. But 500 and run the program. What we'll find is it will generate some numbers, just as we've seen before. So we've got 75, 42, 20, 22, 75, 40, 74 and 22. So if we just remember those very quickly, try and remember those, what you'll find is if we run it again, we should get the exact same values, which we do. When we run it again, we should get the exact same values. So this random number generation, because it's using a seed value of 500 and that wasn't changing in those 3 times that I ran the program, it's going to always make always make the same random numbers. If I leave it to just being blank, it will use a time dependent value. It will use the system time to generate the random numbers we're after. So run it again now without a seed value in there, I will not get the same numbers. And then when I run it at a different time, a few seconds later, again I won't get the same numbers as I had before. In this case, it randomly generated 27 twice. I'll run it again because it's based on a different time now. It's not got the same numbers. It's using the system time now. In fact, you can go and read an article about how a man in the United States hacked the random number generator to rig the lotteries. So in the United States, they used some random number generators for their lottery machines, and he was able to, well, he worked for them. He was an insider, and he was able to hack the numbers for on specific days using specific seeds maybe. It's an interesting read, but yeah, use random number generators to know what the lottery result would be. You can go and find that, read about that. He didn't get away with it in the end. So we've got our random integers appearing, and yeah, as we could potentially get it in order if we were lucky enough. We could keep running this until all of the random numbers generated were actually in ascending order. It might take us a while to do, and you could do you could make a brute force program to keep doing it and find out how many times that would happen. But that's not the aim of this video. The aim of this video is to take a unsorted list and to sort it. So we need to move on to making a bubble sort. So the next subroutine we'll need is a bubble sort. And that's what I'm going to call it, bubble sort. And it's going to get passed in a particular array. I'm going to keep with my naming convention of int array. And it's going to take that and it's going to have to sort through it. So for a starter, we need to compare those pairs of numbers. We need to compare those pairs of numbers. So we're going to make a for loop to do that for us. For loop for the int array length. Now we're also going to do the length -1, because when we get to the very last item in our, I'll demonstrate it. As we get to the very last item in our array, we don't wish to compare it to anything after it. So we compare the first two, then we'd be comparing the second two, the third two, the third, yeah. 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6. We'd be comparing pairs every time. What we don't want to do is compare that last one to an array position that doesn't exist, because then it could cause us to crash. So we're reducing it by 1. We're not interested in checking that last one. And then we're going to have an if statement for doing our comparison, and it's going to be looking at the int array at position I and checking if it is greater than the int array at position I plus 1. So the next one along. Because if the one below is greater than the one above, we need to swap them. If it isn't, we don't need to do anything. So run the program again and let's see an example of what I want to happen. So if we have this, 66 is less than 70, so I don't want them to swap. So I don't want them to do anything. 70 is greater than 36, so I would want those two to swap. So next up we need our swap. So in order to do our swap, I'm going to make a temporary integer, and I'm going to set the int array at position I, the temp integer equal to the one at position I. Then I'm going to set position I to be position I plus 1. So int array at position I is then going to equal in position I plus 1. And finally, in position at I plus 1 equal to that temporary value to swap the two over. Take a copy of what is in there, change what is in there to there, change what is in there to the temporary integer, swapping the two over. So let's run the bubble sort. This isn't a finished bubble sort, by the way, it's just demonstrating what's going on. So the int array there, and we're going to then output the array again. So we've got our random array into integers. We've got an output of that array. We're bubble sorting it, and then we're outputting it again. So we should see a difference in these two outputs. This should be unsorted. This should be semi-sorted. And what I'm going to do is I'm going to put a seed value in again. Let's go for 500 because we had it before. A seed value, so that when we do this test and any future tests, we can see that the values, or the bubble sort is working without having to, well, having the same list every time, because our seed value will be the same. We'll get the same random integers being created again and again and again. to test out our bubble sort. So we should see an unsorted random list, and then we should see a semi-sorted because we've run once through our bubble sort. We don't get to see it very well, so we'll put a right line so we can see one line different from the other. So that's just going to leave a line between the two sets of numbers. They're on the same line, we don't know if they're sorted or not. Okay, so these two are different. So this is our unsorted list, and then this is our semi-sorted list. And just like in the examples we had before, it's moved the largest number over to the right hand side. So if you see this 75 has moved all the way to the right hand side. And that's using one for loop. Now we need to repeat that process for however many items there are, and we will definitely have the list sorted. Or instead of thinking about however many items there are, you could also think about it as long as there's no swaps been made. When no swaps have been made, that's when it's sorted. But as long as we are making swaps along the way, it's unsorted. So the simplest way we can do it is just another for loop, and we're going to nest the for loop that we had already in there. So we'll need some different identifiers. So we'll go for K, and we need to go through the length of the integer array. So we're going to have that 1 repeating over and over and over again. And in fact, just so we can see what's going on, and we can see the various steps, I will put some outputs in here just to slow it down a little bit to let us see what's going on. So we'll put an output at the end of each one of these swap loops, and we'll also just, well, we've got K, so we know which swap time it is. So we're going to have it console write line and say swap swap loop number, and then concatenate it with K plus 1. Now why am I doing K plus 1? Well, K is going to be 0 the first time we do this swap loop, then 1, then 2, so I'm just making it a more user-friendly output, saying that we're on swap loop number 1 rather than swap loop 0. And we can output the array each stage. Output array int array, and I'll put a console read line in as well, so we can do it one step at a time and prove that this is working. Okay, so swap loop number 0, 1, no, it's not done the mathematics. If I put it in brackets, what it was doing, it was concatenating whatever K was, so it was 0 with 1, and it was coming out with that being a little string of 0, 1. So I've put it in brackets so it knows it's got to add 1 to whatever K is now, so we won't get that happening. Okay, so as before, the 75 on the first swap loop has moved to the end. It just so happens that this has got two 75s, but the one of those has moved to the end because it is the largest. We go through loop number 2, and that other 75 is joined over this side. So what should we expect next? We'd expect the 20 to stay where it is, the 22 to stay where it is, the 42 and the 40 to swap, and the 74 and the 22 to swap. So let's see that in action. Okay, so the 40 and 42 swapped. They didn't swap because they were already in the correct order. These two swapped, and these two swapped, and nothing else did because that's already in the correct order. What do we expect to happen next time? No swap, no swap, no swap, no swap, swap. We expect 20 and 42 to swap only. And that's what happened. What do we expect to happen after this one? I expect the 22 to be there. And now I'd expect, well, no changes because I think it's in order. It is still going round because we've not done any sort of efficiency, so it's going round and looping and looping and looping. So that is proof to me that it has worked. So I'm going to just comment those out in case I want to prove it later on. And yeah, if we take the seed value out, we should get that happening again and again and again, no matter the inputs. So in this case, the input list like that, and now we've got an ascending order. How easy is it to change to descending? Well, let's change this greater than symbol to being less than and run the program again. And it's in a descending order now, so it starts off like that and it's going to come like this. So ascending, descending, the bubble sort is just changing the less than to greater than or greater than to less than. So we'll keep it with ascending order there. And we'll just test out with a larger amount of numbers. Let's go for 25. It just goes off the screen, so I'm just going to reduce it down to 22 so we get to see it all on one line and then the line below. Okay, so we got our unsorted random array and then our sorted one. If we do spend time looking through, it has worked. That's the basics of binary bubble sort there. I'm just going to add some labels so I'm able to tell which one's which. Unsorted, and then sorted. With a bright line as well. So I quite clearly separate them no matter how many numbers I've got now. So yeah, unsorted, sorted. Excellent. And I can keep going with much larger numbers, so let's go for 1,000 different integers now. So generate 1,000 different integers from 0 to 99, and then our bubble sort will sort them. Make this smaller. Run it again. Might have a chance of seeing them all on one screen. Yeah, so size 8 font, Lost it now. There it is. Size 8 font or unlisted, unsorted list of 1,000. So it goes from 0 to potentially 9,999. Yeah, quite clearly unsorted. If we just pick on some numbers, yeah, there's a 32 there towards the end of the list. And then here, just a quick spy on it. Well, yeah, you got single digits, double digits, treble digits, and then into the 4 digits worth. Excellent. Sorted, unsorted. So I'm happy that that is working. The last thing to do would be to kind of try and prove how efficient this is. So we could use, well, we'll do that in a different video. We'll do the binary, the big O proofs in a different video, and we'll time how long these different algorithms take. But that is the bubble sort. Go for 10,000 items, 10,000 integers. Might take it a while to output. Yeah, quite a few different numbers. And then here's the start of our sorted bit. And it does seem to have worked still. Yeah, I'm happy that that works. It develops a nice little pattern there of different numbers, number lengths. Go to an extreme. 1 million. Yep, 1 million. See what that comes out with. I anticipate what will happen is it'll create the unsorted list, print them. There'll be a little time gap, and then it'll print the sorted list. So I'm guessing that this is printed the unsorted list, printed the million numbers. Some nice patterns. So these numbers would be generated from 0 to 999 million. No, sorry, apologies. It'd be random numbers from 0 to 10 to 1 less than 10 million. So quite large numbers, but there should just be 1 million of them. It's taking a while to print out the full million. At this point you start to regret it and think you should have chosen 100,000 rather than a million. what you can see is there's not really any pattern to it, so we've got lots of different numbers of all sorts of different sizes being output, so they would have all been generated various different size numbers along the way, and when it goes and sorts it and which starts to output the sorted array, hopefully we'll start to see a pattern. So you notice here it does say sorted in the bottom left here, and it is not outputting it yet. So let's just have a look before we carry on. Yeah, there are numbers of all sorts of different sizes here. Trying to see if I can spot a single digit one while it's doing the bubble sort of it all. Can't spot it. It's like, where's Wally this? Can't spot one. It might be that there's not one on our screen. But you notice that it's not outputting the sorted bit yet, and that's because it's taking it a while to bubble sort a million different things. And in fact, I'm going to pause the video and then re-record when it has done it. Okay, so I scrapped that. Doing a million was proving to take too long. So what I've done is reduced it down to, let's reduce it down to 50,000. Yeah, we'll reduce it down to 50,000. It will still show us the same sort of thing. So run this program now. We'll generate 50,000 random integers in an array. It will output them to the screen, so we'll get to see all of those flashing up on our screen. It will then output the word sorted and then wait a few moments whilst it actually sorts the array. So here's outputting the unsorted array, 50,000 items. And now it's going through and sorting those 50,000, and it will output them. So notice that there's not the patterns aren't, there's no real patterns in these. These are numbers of all different lengths that have been generated. When we sort it, we get nice streaks of lines because they're all sorted. So yeah, we're not going to go through these lists and check every single number. We did a few tests before and we've determined that it's correct. So yeah, ended up with the highest numbers being at the ends all sorted out. So that test worked. In a future video we'll do more on big O notation, and we'll prove that it generally works along the way. But that is the bubble sort. In its simplest form, 2 for loops. One for loop nested inside another. And changing things from ascending to descending, just a case of changing the greater than sign to the less than sign.